So in this video, we're going to do some examples. We're going to get some hypothesis testing done. We're going to connect all the other things we've learned so far about regression, including the coefficient of determination. And we will check out these two and see what they have in common. Okay, so starting from the start here, here's some data from 13 students about how many hours of math homework they spent per week. We also asked them what their final grade was for in this math class in percent. Now, maybe instead of in percent, I will change those to points, because sometimes when we talk about percent and points, it can get a little confusing. So from now on, I'm going to talk about their grade in points, which will actually be easy to convert to percent, because I'm going to make it out of 100 points. So let's look at this. We got some hours and we got some grades. So it says label the points and label the axes. Okay, so to think about this in the beginning, we got to think like, what is the lowest and the highest amount? In terms of hours, it's pretty easy to see. It's from 0 to 10. And probably it'd be best to go by ones then. This is going to be my x-axis. 9 times out of 10, maybe even higher than that, the list 1, or the x value, is going to be our x. So list 1 is x. So here's x, and then here's y. Now our y is going to go from, looks like our lowest number is 20 and our highest number is 100. Well, I'm kind of evaluating our graph paper here, and it looks like we have a 10 by 10. So that means I can easily go 0, 1, 2, 3, all the way to 10 here for my hours of homework per week. Okay, and also, you know, the problem did want you to label it, so we're going to do that too. Hours per week. Okay, that's what we're talking about. Then on the y-axis side, this would be our grade, and our grade is going to be in points or percentages. So here's 10, 20, all the way up to 100. I'm always mindful of how many tick marks I'm given on the worksheet and how best to kind of chop that up. Okay, so now you have, it's for me to look at this at the same time. I have just maybe not enough room here. Oh, I just barely have enough room. Okay, so now I can plot the points and look at the screen at the same time. So 785 is a point right here. 560 is a point right here. This would be a good time to maybe fast forward through the video. 8 and 75, 7 and 80, 10 and 95, 6 and 50. Well, if you're kind of doing this along with me, it's kind of like doing the work together here. 4 and 20, 6 and 65. Nothing really weird in terms of plotting these points. 7 and 70, 8 and 70, 10 and 100, 0 and 20. Not a really good grade there. And 3 and 20. So it looks like there is a positive trend here, but you know, how strong is that positive trend? So now that we've plotted the points and labeled the axis, let's do the linear regression t-test and report the data out here. So I'm going to tell you that before I did this video, so you didn't have to watch me type in all my list 1 and list 2 data, I typed in all my data. So I hit stat and I hit enter, and I typed all the data into list 1, which you can just do by typing it and hitting enter, and then moving over to list 2 and typing all my y data in, or the dependent variable, into list 2. So to get to the linear regression t-test, you click the stat button. You're going to move over to the tests menu, fast to do that by clicking left, and then you're going to find the linear regression t-test, and it's best to scroll up, because if you scroll up, you can find it easily from the bottom here. So the linear regression t-test, and we've got a lot of stuff to write down. Look, we got to write down all of this over here. Now keep all our defaults, because we're going to have our alternative hypothesis is not equal to, and we're going to move just to calculate. We're just going to get this and do the rest by hand. Okay, so here's our t-value, 7.41. We're going to write that down. Our p-value is not 1.3. This is an exponentially small number. So we need to move the decimal 5 spaces to the left, so it's going to be 0.4 zeros and a 1. There's 11 degrees of freedom. We'll need that for our table that we're going to look at. Then we're going to copy down the a value, the b value, and the r and the r squared value. We're going to leave this s value until the very last unit where we evaluate the standard error of the estimate. So let's copy down all of these numbers, and I have happened to do so on a separate piece of paper so I can write this in. So this is, the t is 7.4, the p value is 0.1234 and 1. Technically it's 1.3, but the 3 doesn't push the 1 up, so this is an appropriate p-value. Please do not write your p-values as exponentially notated numbers. Write them as decimals. That way we can compare them to alpha correctly. 11 degrees of freedom, because we had 13 students, and 13 minus 2 is 11. And our A value is 5.7. Our B value is 9.1. Our R value is 0.91, and our R squared value is 0.83. Now it says get the line of best fit on your calc and sketch it on your graph. Okay, so I'm going to use my calculator to show me where my line of best fit is. And I need to see this because I want to see where the line is going through the points or around the points. Now, I clicked the y equals key, and I noticed that I had an equation in from a previous problem, so I'm going to hit clear. The equation I want right here is going to be my A value, my 5.7, see that's my A value, plus, since this 9.1 is positive, 9.1. And then I'm going to click the X key. So this is my line of best fit, or the least squares regression line. Now you'll notice that the plot 1 is black. That's really good. And if I want to double check, I can click second y equals, and I can see the plot 1 is on. We want that. It looks like a scatter plot. And we're going to pick list 1 and list 2 with this square dot, and all the other plots are off. If I did this right and fixed my window, which I haven't done yet, I will see the dots on the screen and the line going through the dots. Now let's follow the window to what I did here. My x minimum is 0, my x maximum was 100. I'm going to hit enter. And then the x scale from going from 0 to, oh wait, it's not 0 to 100, sorry, it's 0 to 10, enter, by 1s, enter. So x is 0, x maximum is 10, x scale is 1, and the y minimum is 0, the y maximum is 100, and the y scale is 10. Okay, so that's kind of nice. Now I have the window matching the exact picture that I've drawn by hand. Now if I move this over and hit graph, you'll see all the dots rendered, and you'll see the line of best fit going through those dots pretty well. So it looks like I'm starting, and I can use my y-intercept, my 5.7. Looks like I'm starting around a 5.7, and since I'm starting around a 5.7, I can then kind of make a trajectory to this dot right here, and I'll do my best to draw a straight line. Obviously it might be nice if you're doing this by hand to use a ruler. Alright, that will help a little bit. Okay, so what is the line of best fit? Well, the line of best fit is going to be my y hat is equal to that 5.7, that's my y-intercept, plus the 9.1 x. So this is my line of best fit for my equation. Now it says write the line of best fit and the equation above into words and match the context of the problem. This is a translation problem. So I'm going to have to take this 5.7 and 9.1 and add it into context. So starting, we're going to start with the word starting. Okay, starting at 5.7. Now I need units here. And since this y-intercept is a y, it's going to be y units. Starting at 5.7 points, you could also say percent if you'd like to. Starting at 5.7 points, you add, you could also say other synonyms for add, like go up or move forward. You add 9.1. Now this is a slope, and slope is y over x, or change in y over change in x, y minus y over x minus x. Lots of ways to write the slope equation, but it's change of y over change in x, so your units have to be in y over x. So you add 9.1 points, okay, now that's the y, per, that's the, now we're going into the denominator here, per hours per week. So that is translating your line of best fit into a sentence that anyone can understand. Basically, by doing nothing, you get 5.7 points in the class according to our trend line, and we add about 9.1 points to your grade for every hour of math homework you do per week. So if you want to get an A, you're going to have to put in roughly 9 to 10 hours. So now what we get to do, remember all of the other stuff we wrote down, the T, the P, the degrees of freedom, the R, and the R squared? Man, now we get to play with hypothesis testing. So this is going to be important to have your chart. The chart that I had you download and maybe print out or have in front of you for the previous video. Now the chart has a T chart to it, and it also has an R chart to it. So these two separate problems are going to be hypothesis tests with the same conclusion. Now you'll note in step number 5, I have you write the null and alternative hypothesis. And the null hypothesis is rho is equal to 0, and the alternative is rho is not equal to 0. These are always your null and alternative hypothesis, because the null hypothesis says, there's no correlation, and the alternative says, yes, there is a strong correlation here. The correlation is not 0, and P is, or this P looks like a letter P, but it's really rho, RHO, Greek letter R. So let's move on to the t-test, steps 2 through 5. Okay, now it's important to note that off to the side, you're going to use this for both the T and the R step. You have to know your degrees of freedom. Your degrees of freedom is 11. I'm writing it here so we don't have to scroll up all the time. Our alpha in this case is always 5%. If not mentioned, alpha is 5%. And then we're going to make sure we're in the two-tail row. And the reason why we're in the two-tail row, tail row, is because we're using a two-tail test. Not equal to is two-tail. So be sure of that. So what we're going to do in step 2 is find our critical value from the t-chart. Okay, so our critical value from the t-chart is going to be plus or minus our degrees of freedom of 11 at a two-tail 5%. So let's go to our t-chart. Boop. And here we are at the t-chart. Okay, I'm going to scroll down, get my highlighter out, because that's the best way to kind of highlight in on what we're doing here. So we're at 11 degrees of freedom. Okay, we're at a two-tail 5%. So this critical value is going to be plus or minus 2.201, which means that if we're more than that many standard deviations away from that norm on the t-curve, we are going to reject the null hypothesis. So back to where we were going. Okay, so the critical value, we did find it as plus or minus 2.201. Don't forget the plus minus. Gonna have to mark you down if you do. And then the t value that was given in, this would be step 3. The t value that was given on the calculator is 7.4, which is much higher than 2.201. Now step 4 is to draw a t-curve, which you can draw as a normal curve, but again, a t-curve is based on sample size. So we have a 0 in the middle here. We're going to have two shaded zones here, okay? And those two shaded zones are going to start at positive 2.201, mark that, and negative 2.201, mark that. And as long as our flag, our 7.4, is in the shaded zone, we get to reject the null hypothesis. And heck yeah, look at that. That is at our 7.4 right there. There's our beautiful flag. And that 7.4 then tells us, since we're in the critical region, we reject the null hypothesis. So I'm going to shorten up our conclusion, which is step 5. And you can too, since space is at a premium. Since 2.201 is less than 7.4, you could write it the other way around. 7.4 is greater than 2.201. We reject the null hypothesis. Okay, we reject the null hypothesis. Yep. So there's your conclusion that we did with our t-test. Now we're going to show the r-test. And the r-test should match this result here. So step 2, the r-test, is to get our critical value. So we're going to, again, maybe pre-write our critical value as the plus or minus of whatever the value says on the table for 11 degrees of freedom at a 5% alpha for two-tail. So let's go take a look again at our chart. Now this is the T-chart, so on the other page is the Pearson correlation critical value table, known as the R-chart. So we're going to go to 11 degrees of freedom. Okay, this one's going to be a little bit trickier to get everything in on the same page. So there's 11 degrees of freedom. Oh, I got to click very carefully here. And I have now two-tailed 5%. So that means plus or minus 0.553 or 55% if your R value is bigger than this or lower than the negative number in case it's a negative correlation, we get to reject the null hypothesis. Okay, back to the problem. Okay, so here we have our problem. We found that from the chart it was plus or minus 0.553. This is step 2. Step 3 would be figuring out our R value, which the calculator gives us as 0.91. Wow, that is much higher than this. Well, here is step 4. It's not a normal curve, it is a continuum of possible R values. So we can go from -1 to 1, and our shaded zone in this case is going to be here at negative, actually it's going to be much bigger. This is going to be negative 0.553. It's almost half the, it's a little bit more than 50%, so it's going to take up a little bit more than half the space here. Well, actually this one will be a little bit less than half the space. Pardon me for that. All right, well, I'm just going to leave it 553, all right, because it's, 45 about, let me see there. Yeah, it's 45% or 55 away from the 0, so it's about 45% of this line. Oof. All right, sorry about the mental mistakes there. But what we're looking for is where to plant our flag. 0.91. Yep, I'm going to plant it right here. Bloop. There we go. Planting it right there, and that basically tells me I am in the critical region, which means I get to reject the null hypothesis. Since 0.91 is greater than 0.553, we reject the null hypothesis. All right. Now, you're thinking we're done, but we got one more step to do for this problem. We're going to perform a p-test. Conclusion using the p-value from above. Okay, so using the p-value from above, what we're going to do is we're going to say since, and let's see, that p-value is 0.4 zeros and a 1. Well, how does that compare versus the alpha? The alpha was 5%. Well, it was less than that. So since the p-value is less than alpha, so since p is less than alpha, let's write the numbers down. That would be a little bit helpful here, since I'm letting you out of all the other writing. Since p is less than alpha, we reject null hypothesis. All right. We definitely have sufficient evidence to reject the null hypothesis. And look at that. We have 3 conclusions, and these 3 conclusions basically set up the same results. We reject the null hypothesis in every single setting. No matter how we wrote our inequalities, we could have wrote this as since 0.553 is less than 0.91, and we could have also compared alpha to p and said since alpha is greater than p, you're still going to reject the null hypothesis in all 3 cases. All right, coefficient of determination. Let's figure this out here. The r squared, okay, was equal to 0.83. I'm just going to put this off to the side, and let's think about this here. Let's think 0.83. Well, that means that 83%, and this goes back to some previous videos here, 83% of the grade's variation, and this is the y value here, 83% of the y's variation is explained by the variation in the hours of homework per week. All right, so that's the first part of our answer here, because the format of this problem goes with the percentage of the y's variation is explained by the variation in the x variable, okay? Because the x affects the y variable. It's the difference between the independent, which is the x, and the dependent, which is the y. And it follows this format pretty straightforwardly, okay? 83% of the grade's variation is explained by the variation of how much homework you do per week. You know, it's an input-output situation where the input is your homework and the output is your grade. Now, I do need to add that 17% is unexplained. So maybe there's more to the story than just homework, which is always true. We can only look at two variables at the same time when doing this kind of work here. We can't do more than two, so there has to be an unexplained portion of this. You know, we can focus on other variables that wouldn't have such a big effect, but it feels like putting the time in is really going to give you the biggest effect. 17% could be natural ability, 17% could be, you know, how far you have to drive to school or how hard you're working on other classes at the same semester. So it really does have some extraneous things. Okay, now we're going to talk about the next problem. I know we've already clocked in a lot of time on this problem so far, but it really helps to have another example just like this one as we move on to the next problem. So here's how I'm going to make this problem a little shorter. I'm going to pause the video we're recording here, and I'm going to plot all my points. I'm going to enter all my values into the calculator, and that way we can pick up without doing all of that minutia on this roll. And I really think that maybe you should try to do as much as you can before you unpause the video here to see how far you can get. Although this problem is a little different, it does have a lot of similarities. Okay, as promised, I have basically labeled my x and y axis here because in this case we are looking at 11 students and how many hours of non-academic screen time they spent per day. So I can see that I accidentally wrote my x-axis as hours per week, but it really should be hours per day, not per week. But happily I was able to keep the x values the same as I did in the previous graph. Notice I'm going from 0 to 10, and also the grade in points or percent from 0 through 100. And so here are my points. Looks like this is following a downward trend. And I've also, as promised, typed this into my calculator. So here are my values, and I've triple checked to make sure that they are exactly the right values. And that's always good to do that. Please double and triple check your values. Okay, so it's time to play this linear regression t-test. So click on the stat button, move over to tests, move up to the linear regression t-test. Okay, and we want all the defaults, list 1, list 2, two-tail, calculate. Let's move down to that. If you have a very old graphing calculator, it'll just spit out the data. Okay, looks like our t-value is negative 4.36. Our p-value is very, very small. 9 degrees of freedom because we had 11 students, 11 minus 2. And here we have our a value, which is 103.26, and our b value is negative 10.3. We're going to skip over the s and write down our r and r squared values. So let's do that. Now, you can look at this on your own calculator. I'm hoping you're doing this along with me. So this is negative 4.4. Our p-value is 0.0018, or you can write just 002, the first number past the zeros. Let's go with 9 degrees of freedom. Our a value was 103. Let's round that to 103.3. And then this is negative 10.3. All right, now our r value here is negative 0.82, and our r squared value is 0.68. All right, now to sketch the line of best fit on your calculator, sketch it on your graph. The line of best fit is, or our y hat line, is created by our a value, which is our start, 103.3, and our b value, since it's negative, we're going to subtract the 10.3x. Don't forget your x. You could also put plus negative. I like to just put subtraction. And then now we're going to go to our y equals. Our y equals, we have to clear this old line out. Don't forget to do that. I still have sometimes people putting the same line on all 4 graphs. But we have to put in our new line, 103.3 minus 10.3x. And then the x key is under the mode key. Now, it's best to check your window, and we are still going from 0 to 10 by 1s and 0 to 100 by 10s. You will have to probably change your window from time to time, so always feel free to check it. Now, if you hit graph, there's our downward trajectory. It looks like it kind of skims past all these dots and intersects this one and goes right to the corner. So I'm going to try to do that with my line of best fit. Now, again, if you're doing this by hand, you should probably try to use a ruler. All right, because I'm not going to use a ruler. And since I started at 103.3, that would kind of make sense to be a little bit higher there. But again, use a ruler. The ruler will help you out and make it look nice. And if I'm grading it, you may want to make it look nice. Okay, so now we're going to write the line of best fit and the equation above into words that match the context of the problem. So I'm going to translate this. So how am I going to translate it? Oh, okay, so we're going to starting, and we're going to start always with the word starting at 103.3 points or percent. Okay, wow, you would get a perfect grade if you just didn't do any non-academic screen time per day, haha. So starting at 103.3 points, you drop or go down or subtract any synonym that would mean this subtraction. So let's just write down subtract, why not? You subtract 10.3. Now this again is a slope. Slope is y over x. So slope is your y units, so 103 points over per, and then your x units in this case. Hours of screen time, SCR, screen time, sorry to kind of budge that in there, screen time per day. So 10 hours of non-academic screen time is not going to give you a very good grade. That's a lot of time not working on in school. So that is your translation. Now let's do all the hypothesis tests before we conclude with the coefficient of determination. So, what's our null and alternative? Well, the same thing, the same thing every day. It's rho equals 0 and rho is not equal to 0. So there's your null and alternative. We don't have to like bring that up anymore. But now we're going to talk about our t-test and r-test. Now, it's important, since I don't want to keep scrolling up all the time, to have my degrees of freedom off to the side here. So I'm going to look up 9 degrees of freedom with a 5% alpha. If alpha isn't stated, assume 5%. And we're always going to go to tail because we're going to be rocking the not equal to alternative hypothesis. So let's go to our t-chart. Our t-chart here has, I want to go 9 degrees of freedom. And I want that 9 degrees of freedom to then have a two-tail 5%. So this means my critical values are plus or minus 2.262. Did you remember the plus and minus? That is something I don't want to have to mark wrong on your paper. So let's do this for our t-test here. Critical value, step 2. Critical value is plus or minus 2.262. And our test value from the calculator was negative 4.4. So we're going to have our, whoa, let's try that again. All right. There we go. There's a little bit better t-curve right there based on the normal curve based on degrees of freedom. So we have 0 standard deviations from the norm, but our critical value is going to be at negative and positive 2.262. So if we are inside of our critical region based on these critical values, we're going to get to reject the null hypothesis. And yes, we are. There's my flag pointing at negative 4.4. Woo! Negative 4.4. So, ladies and gentlemen, what this means is that we get to reject the null hypothesis since negative 4.4 is less than negative 2.262. Be sure that your inequalities are in the correct order. You could have also written negative 2.262 is greater than negative 4.4. We reject null hypothesis. Okay, we reject the null hypothesis. Okay. So we're now going to look at the R test. So we're going to have our critical values here, plus or minus where the 9 degrees of freedom has the two-tail alpha of 0.05. Let's take a look at our R test. Okay, so we're not on the t-test distribution chart. Go to the R chart here, R chart, which we're going to look at 9 degrees of freedom. Okay, so here's 9 degrees of freedom. Here's our two-tailed 5%, which is going to mean we need a higher R value than 0.602 or a lower value than negative 0.602. So here is the answer. Let's go with that. We've got our plus or minus 0.602. Our R value that we found from the calculator was, whoa, negative 0.82. All right, so on the R number line here that goes from -1 to 1. I guess there wouldn't be arrows here because the arrows would, I mean, this doesn't go forever. So let's make a segment instead of a line. So -1 to 1, 0. All right, let's go and shade. Now this is going to be at 0.602, so this is about here, and this is about here, about 60% away from 0 in both cases. So negative 0.602 and positive 0.602. Okay, so where is our flag? It's at negative 0.82, so we're here, right there at negative, and I do want to label this as well. Always label your flags and your shaded critical regions and the critical values. All right, since negative 0.82 is less than negative 0.602, we will reject the null hypothesis. All right, so there we go. We reject the null hypothesis. Okay, so can we do more? Is there more tests we can possibly do? Yes, we can do a p-test. So since, and let's look at our p-value here. Our p-value is 0.0018, and our alpha is 0.05, and since our p is less than alpha, we are also going to reject the null hypothesis. Huh. Now, do you see the connection between all three of these? Yup, all three same results, just like on the previous page. But you'll notice on the previous page, I mean, you can look at it, trust me, you're rejecting as well. So what do these two graphs have in common? Well, I mean, they're both talking about work hours of something and math work, but these are two examples of strong correlation, just like the title of the video says. These are examples of strong correlation. The first problem that we did, the first example, was strong positive correlation, and this example was strong negative correlation. All right, we can have strong positive and strong negative, and we now need to finish this up by talking about the coefficient of determination. Now our R for this problem was, or R squared for this problem, let's put this off to the side just so we don't have to look up there, was 0.68, so we can say 68% of the variation in, now in this case our Y, in the grade is explained, sorry, that handwriting's a little sloppy there. 68% of the variation of the grade is explained by the variation in hours of, not per, hours of homework spent per, or not homework in this case, that was the previous problem. Gosh. How hours of screen time per day. All right, so the more hours of non-academic screen time you spend per day, the lower your grade's going to get. But look at this R value, R squared value. This R squared value was not very close to 100% like the last one was. So what we have now is 32% is unexplained. Alright, so there's a lot more that could be affecting this grade than just the non-academic screen time. So that's good to always point out. So you made it, folks. You made it through a long video here, but we've got another one that's going to talk about, I don't know, maybe instead of strong correlations, we're going to look at some other types. So thank you for watching, and buckle up for the next 2 examples that will help you with your homework and tests and final exams.